Dear learners, once again welcome to week 7 lecture 1. So, before going to this I would just briefly discuss that till date whatever we have covered, that in week 1 I have developed or discussed about the composites material and then the basic cell equations. Week 2 was related to the development of theorem of surfaces and strains. Under the week 3, governing equations for a doubly curved shell was developed. Under week 4, discussions and various special cases have been discussed. Week 5, that bending solution and MATLAB program was elaborated. Week 6, in that specifically that extended Kantorovich method and Levy solutions were presented, and this week 7 I am going to discuss about the buckling of the shells, and week 8 I shall develop the 3-dimensional solutions. First of all, why we want to do or we want to study the buckling of shells? So, this is the statement given by David Bushell, who is a pioneer, I would like to say, that has done lot of work in shell buckling, both experimentally as well as theoretical, and there is a website shellbuckling.com that is devoted to the analysis of buckling of shells, various type of shells, and papers related and other experimental works is discussed in detail, shellbuckling.com. So, it was prepared by David Bushell. In order to produce efficient or reliable design and to avoid unexpected catastrophic failure of structure, of which then shell are important component. So, basically it means that whereas the cell are important component, we are interested to produce a efficient reliable designs. It is very important basically to study buckling in cell as compared to plates or beams. The reason behind that, because shells are very thin and buckling may occur due to variety of reasons. In case of a plate or in case of a beam, it is due to just only the axial compressive load, but in shell it is besides the axial compressive load, the buckling may be due to the external pressure or buckling may be due to the combined effect, or there may be a local buckling due to the concentrated load, or buckling may be due to some geometrical imperfections, may be due to the earthquake, may be due to the temperature, may be due to the initial stresses or residual stresses. So, there are variety of reasons due to which buckling may happen. Before going into the subject, that buckling of shell, let us review that today is 28th December that I am recording this video. So, on the scoop as it is showing, there are 18,000 articles in which the buckling of shells are discussed, and they may be theoretical, may be experimental, may be functionally graded, may be nano carbon tubes, may be isotropic metals, or may be different kind that due to imperfections or due to different geometry, different boundary conditions. So, maybe shells may be toroidal cells, spherical cells, cylindrical cells, any kind of shells. So, it is shown that 18,000 articles are devoted to the, out of which 10,000 articles are related to the buckling of cylindrical shells. So, you can see that very huge amount as a portion, at least 50% work is related to the buckling of cylindrical shells. So, buckling of cylindrical shell is very, I would like to say, that important topic. Previously, in the case of bending, I said that cylindrical shell is the most simple shape. So, lot of work has been done in that direction. But when we talk about buckling, I would like to say that cylindrical shell is not simple. When you compare the experimental results with the theoretical results, there is high mismatch. So, that is the reason that a small imperfection in the metals cylinder or may cause entire different state of a buckling. The major reason is that whatever we are predicting, let us say the critical load of buckling, but in practically or actual situations it happens very early as predicted. So, buckling may be analyzed in 3 steps. One is the pre-buckling, just before the buckling, and the buckling and post-buckling after the buckling. So, I think in plates nobody studied about the post buckling, very less work is related to post buckling or pre buckling kind of thing, you have only heard about the buckling. But in the shell these terms are very frequently used and lot of paper is devoted to all 3, means pre buckling, buckling stages and post buckling stages in the shells. So, there may be some experimental works are available, theoretical works are available, there may be some empirical formulas are used, and then the some when the after 1980s or 90 computer codes were used to study the buckling of cells. So, what do you mean by a buckling? When we do call it that shell is buckled or a plate is buckled, it means, I think, undergraduate level the concept of column buckling is presently like that. If a column is there and if you apply a axial pressure P and maybe you may say any boundary condition, so it may try to bend like this. So, what is said that, let us say a column is there and you are trying to put the axial pressure over there. So, you are increasing the pressure by delta. So, after some time a point is reached, if you add further delta it changes the shape, means a large deflection takes place. So, sudden change of a shape or a bending due to a load, that is called a buckling. So, buckling of beams and plates are easy as compared to shell, which I have told you that in the case of a beam and plate, buckling is comparatively very easy and only one type of buckling on a compressive stress can be done. But in the shell, why the buckling in the shells is difficult and why shells buckles more frequently than the plate? The reason behind that, since we are using always thin shells. So, thin shells are used for structural applications. Then cell can absorb a large amount of membrane energy without deforming much, because when we say that our cell is thin, so membrane, membrane theory of cells, so where cell is subjected to the in plane stretching, so it can take more membrane energy, can store. So, there will be less deformation, but due to some loading conditions, boundary conditions, some geometrical parameters, if this membrane energy converted into a bending energy or it resists only very little amount of bending energy. So, due to the bending effect, the large deflections may take place. So, but the cells cannot absorb more bending energy. If a shell is loaded in such a way that most of the strain energy in the form of membrane compression, then the shell may buckle. Means when you are going to subject a shell under the compressive stress, then shell may buckle. So, it can convert the strain energy or the membrane energy into the bending energy. So, buckling of a shell depending upon the loading of the shell, geometry of the shell and the material properties of the shell. These are the important parameters, and further the imperfections we can say that in the shells, because during the manufacturing, let us say it is a circular cylinder, but along the length it may be slightly oval, it may be not completely circle. So, due to that effect, that is known as imperfection, cause a buckling. And shell is thin, so the generally shell are buckled more frequently. So, there is a graph that axial loading and the end shortening. Let us say we have a cylinder, cylindrical shells, very thin cylindrical metal shell. So, in this lecture first I will discuss about isotropic shell, that how the buckling loads are affecting the end shortening or the behavior of the shells, isotropic shells. Then I shall discuss the behavior of a composite shells. So, let us say a metal cylinder or a isotropic cylinder and it is subjected to an axial stress. So, if you increase the axial stress, so slightly its length is decreasing and a point, so it follow a fundamental equation of equilibrium. So, if you remove that, then if you reach a point A, that is known as limit load, there it start buckling, slightly bulging will come up near the edge. So, near the edge at point A, bulging will take place. So, a state is reached that, or I would like to say first ring come up. So, that is known as limit load, and if you start further increasing, then a point B come up, and that point is a bifurcation point. Why there is this bifurcation point? So, basically it may follow two routes. One route is B to C, another route is B to D. If it follows a B to C, so let us say from O to A, shell deforms axis symmetrically along the equilibrium. Then A to B, it deforms axis symmetrically, but B to C, if it follows this path, it bifurcate and further deforms axis symmetrically. But if follows a path B to D, it may deform non-axis symmetrically and the behavior looks like this. They are no longer remain axis symmetry. So, depending upon the imperfections and many other parameters, they may follow any path, either this. So, but we can check through the experiment. So, from this point they may go to two different routes. There is a graph that axial load limits and total displacement corresponding to the load. So, if a cylinder is perfect or a perfect shell, then a black curve will follow. A point B will come up early, bifurcation point, and point A limit load comes up later. When we have a imperfection, means instead of a circular it is slightly oval or some geometric boundary condition is means some defects are there, then it will follow a dotted straight line which is far below this black line, and lambda s is corresponding to limit load to the imperfect shell, and lambda c is basically bifurcation load, and lambda l is the limit load. So, this is the graph. So, now we can study that a shell having imperfection and a perfect shell. In real life, all shells are imperfect. So, we can see this graph because When it is linear, so the initial displacements is very small. So, we can say that up to the point B it is starting from here only, because the deflection is very small. So, we can see that this graph is represented like 0 to B is straight line, and then it is coming line B to D, and for the imperfect shell it goes like this, the red line. So, from this graph it is clearly seen that for the imperfect cells the buckling load is smaller compared to the theoretical or a perfect shell. That is why there is a mismatch between the theoretical and experimental results, because theoretically we assume it is a perfect cylinder, there is no imperfections, or the boundary conditions are perfectly applied if you say clamped or if you say free, but in real situation this may not be true. So, for that cases buckling load may be different, and it has been also found that buckling load is very low, means experimentally observed that buckling load is very low compared to the theoretical load. So, there are various type of bifurcations buckling, like when we have a neutral post buckling, then graph will look like this for a imperfect one, black one is for the perfect one. When we have a unsymmetric, so basically unsymmetric post buckling, then black line is for a perfect cylinder and dotted one for a imperfect one. Then we have a stable and symmetric, and then the unstable. So, in this way the different bifurcation processes are defined for the case of isotropic cylinders. When we talk about the orthotropic or a laminated one, then we have to think about that, because the composite laminates are brittle in nature, they are not like a metal like elastic, plastic zone or a local buckling effect. So, before going to there, during a test, that which I am saying, that test of even a very carefully made cylinder on an isolated buckling initially appears at an average stress considerably below the predicted bifurcation value. Like there are number of work presented in the literature, it has been done that they have developed, made a very perfect cylinder in the laboratory and tested on the ideal conditions. Still the results were far away from the theoretical one. So, it is not that only the imperfections and something, but still there are some parameters which are governing that actual buckling of the shells. So, buckling of a shell is very important, and most of the times very big cylindrical tanks, water tanks, LPG storage tanks, nuclear reactor tanks, all are very big tanks. If we do not study the buckling effect very carefully, so very small load they may buckle and may cause to hazardous effects. So, because when it is a gasoline or it is a nuclear reactor, then it is harmful to nearby areas also. So, we can see that in one of the graph, basically this I have just taken from that Bunchel paper, that David Bunchel paper, that classical theory predicted basically this straight line, whereas the experimental results comes here. So, you can see that very low range, and then experimental oblique theoretically it is coming 0.605 EH by A, where A by H is radius to thickness ratio, A is known as the radius to thickness ratio. So, critical load theoretically is predicted like this. So, it is coming very low. So, our aim is to find out. So, most of the books, if you see in the literature, that experimental buckling of shells are discussed a lot, that from the starting I think 1970s or 60s, even I think after 1950s, lot of work has been done on the experimental buckling of the shells. Now, I am going to discuss about the composite shells, laminated cylindrical shells which are made of composite materials. So, in the metal or in the isotropic materials, because they are elastic materials, and the concept of local buckling comes into the picture. What happens if isotropic metals or the shells, they can take more loads through skin buckling or the local buckling effect. So, actually it is not going to fail the structure, just a small dent, like if this is your cylinder. So, because of this, maybe small wrinkles kind of thing may come up. So, they may take more load compared to the designed one, and they can even that perform their functions without failing. But as we know that composite materials are not elastic or ductile, so they cannot take more loads, because the phenomena of local buckling may not happen in that case. And then concept of imperfections of the composite cylinders, because in the case of metals we know that type of imperfections may happen, but in the case of composite cylinders there may be a different type of imperfections may present, like maybe due to the variability of your angles or delamination or the voids or maybe some other effects. So, due to that there may be imperfections may come up. So, that need to be studied, and lot of work has been done in that direction. Then the third concept, that sensitivity of imperfections. So, I have not discussed in that for the case of isotropic material, that imperfections play a very important role, and specifically that cylindrical shell is very buckling of cylindrical shell is very sensitive to the imperfections. Slight imperfections may lead to a different buckling, critical buckling load. So, in this way these are the some points which need to be addressed when we study the buckling of a cylindrical shells. And lot of work has been done, and through the course it has been find out that laminated shells or composite shells are less sensitive to the imperfections. And they have just I think there was a graph was presented that between a winding angle, means the fiber angle, and the critical load, and graph is plotted that taking the different imperfection factors, and it is showing that these are less sensitive to geometric imperfections. But the concept of delamination between the layers, if there is a small void, small delamination takes place in that area, that may cause loss in stiffness and further may be change in the buckling load. So, the theoretical model, the way we have developed is similar, there is no much difference, but experimentally yes, the other factors can be analyzed and can be found it out. So, in that case, in the case of a buckling, semi-empirical formulas were designed, that designers can use those semi-empirical formulas to know the buckling loads, critical buckling loads, to design the thickness of the cell, or to analyze that shell under different loading and boundary conditions. So, I will first discuss a standard formulation, partial differential equations. These we have developed in week 3 lectures. There we have developed these governing equations, and I think in lecture 4 and 5 we have studied the bending, free vibration by considering only the linear terms. We did not consider non-linear terms, we have taken it all is 0. But for the case of buckling, we are going to consider these non-linear terms. So, in the first equation we have 2 terms, in the second equation also we have 2 terms, third and fourth we do not have, but in the fifth equations we have, yes, 4 terms are there. So, these are our governing equations with the non-linear terms. So, if somebody is interested to study a generalized buckling behavior of a doubly curved shell, then these equations are perfect and then one can use that. as I have said that cylindrical shells are studied mostly, and for our present case, for basically explanation point of view, I will also use that cylindrical shell. So, for the cylindrical shell, these governing equations are reduces to like this. So, let me go back. Because in cylindrical shell, Lemma parameter A1 is 1, A2 is R, R1 is infinity and R2 is R. So, if you follow this thing, so the first term will not contribute because it is A1 by R1. Again n tilde 1 2, this term will also not contribute. So, in the first equation there will be, for the case of a cylindrical shell, there will be no contribution of nonlinear terms as well as the contribution of bending shear stress. But in the second equation, this term will contribute, and in this term will be taken off. Similarly, in the fifth equation, this will not contribute, this will contribute, this will contribute, this will not contribute, this will not contribute, and again they will contribute. So, by following this procedure, the final governing equations are represented like this. I have done some changes here, that in literature, most of the books, the equation number 5th in present case is kept at third position, the W. So, we used to go U, V, basically first equation corresponding to U, second is corresponding to V, third equation corresponding to W, fourth is corresponding to psi, this is corresponding to psi 2, rotation variables. In the most of the cases or the books, equations are presented like this. Now, you can see that here in the third equation, n hat 1 1 r times w comma x into derivative of x. So, it is whole derivative with respect to x. So, if we open it, that we say that r will get cancelled out, is not a function of x, then n hat w comma x into comma x. So, we can say that first function as it is differentiation of second function plus w comma x hat is differentiation of first function. So, mathematically definitely this term will exist, w comma x n hat comma 1 1 x. But in most of the practical applications, we take that our axial load is constant. Whatever you are applying a axial pressure, it is constant over the circumference, or a external uniform pressure. So, they are not a function. So, these terms can be 0, but definitely if you say that even over the circumference, they may follow some variation loading, then you have to consider. So, it is a very generalized case, but in the most of the books in which you have buckling of shell is studied, so only the first term is considered, because we consider the axial load is constant, it is not a function of x. So, when it is not a function of x, that is 0. Same way, the second term is a function of theta. So, first function as it is differentiation of second function, and then again n 2 2 comma theta, that circumferential in plane stress resultant is a function of theta. For the case of buckling, we also do not consider, so we do not take this term. Why I am telling you this term, like graduate student or a postgraduate student, when they do it mathematically, okay, then they can open it like this and say that okay, I have these terms, but when I go to a journal article or a book, I do not find these terms. So, we must know these things, why we are putting these are 0. Same way, n tilde 1 2 for the this that n tilde 1 2 and n tilde 2 1 are same. Actually, it is n tilde 1 2, it is n tilde 2 1, but the definition is same. So, we have kept it same, and ultimately the contribution of n tilde 1 2 and n tilde 1 2 are presented here, and final equations. One more thing, that we know that qx can be represented in terms of moment, and from here q theta can be represented. So, in most of the cases these 5 equations are converted into 3 equations, because it is when you have a 5 equations, then you have to solve 5 equations altogether, because we know that qx and q theta can be expressed like this. So, you can direct means substitute it there. So, you will have to solve only 3 equations. So, in this way that it reduces to your classical shell theory. So, most of the cases, though it was a general application, but when we go for a buckling, qx q theta are expressed in terms of mx m theta and substituted into equation number 2 and equation number 3. So, again equation number 1, equation number 2 and equation number 3, and equation number 4 and equation number 5. So, but in the present case I have tried to keep all 5 equations together, no need to, because when we do so, then the boundary condition need to be reduced. So, for that purpose I have kept all 5 equations. For us it does not matter whether we solve a 3 equations together or a 5 equations together. Then finally, final form of governing equations for buckling of cylindrical shell. In week 5, I have also given the concept of infinite shell panel and finite shell panel. So, even after that, after this step, these equations may be further reduced to infinite shell panel, means when a shell is very long along x directions, finite shell panel when a shell is having shell panel is finite length, or maybe even for the case of buckling complete cylinder, generally cylindrical shell, complete cylinder is studied like this. So, in that case there may be again 2 variety, short cylinders and then long cylinders. So, these equations are valid, means basically we can convert using further approximation, that when we talk about a complete cylinder, when say we will be going to say that it is axis symmetry. So, in that case derivative theta will also vanish. So, equations will be further simplified. Now, we try to, in the case of a bending, I think when I did a special cases, that is cylinder under internal pressure. So, I have used only 3 equations, that n theta, third equation up to there, 3 equations, number 1, number 2 and number 3 here. So, from here n theta r gives to qz, and subjecting back to second and third, we can solve the stress resultant and finally do that. But when we are interested to a buckling, though it may be a cylinder under external pressure, so still we cannot directly use the in the terms of stress resultant. We have to convert first into a primary displacement form. So, for that purpose, these 5 equations, the important concept is here when we go for a buckling. So, basically the nonlinear term in nxx definition, mxx definition is not considered. So, initially it was nxx is like that, a times of 0 L plus b times of E hat plus again there was some a times of epsilon NL, alpha beta gamma was there, here alpha beta, here alpha beta. So, this term is not considering, but if we want to do a nonlinear study, like load deflection curve, bifurcation curves and all these things, then we may consider these nonlinear terms also. So, for that purpose we completely open up to nonlinear terms and going to solve. That is basically nonlinear bending, vibration. In that way we consider all these things and solve completely. But for the case of buckling, nx and mx theta considered up to here, and q theta, qx is written here. So, definition of aij, bij and dij alpha beta is written here. I have written a very generalized definition. So, you know that for the case of a cylinder, alpha is your x, beta is your theta. So, r alpha is your infinity and r beta, r theta is your r. So, basically when we say aij alpha beta or a121, a121 means minus h by 2 to plus h by 2, q11 1 plus z by r 2 into 1 plus z by r 1 into minus 1. So, r 1 is infinity, this will not exist and this will exist there. When we say 1 2, then this will not exist 1 and this will exist. So, in this way, that in the lecture 5 I have explicitly did that more terms, how a11, a12, a13, but in a combined form which we have expressed in the lecture 4, that we can write aij and finally evaluate a number and put it there or in some expression form. So, it is very general expression and very useful expression for making the program. So, we have written all the index properly, so that putting the proper alpha beta you can find out these numbers, that what will be their definition. So, it will be a complete form. So, less number of unknowns will be there in the final governing equation. So, if you use this concept nxx, mxx and substitute into above governing equations, okay, before going to there we must know what are 0L. For that our present case, gamma and so on. So, this is epsilon 110L for a general shell is presented like this, but for our present case cylindrical shell it reduces to this much. Similarly, epsilon 11 hat, this term will vanish and only this will exist. Epsilon 22 this, epsilon 22 hat this, gamma 120, gamma 120. Basically, we can say that 1 and 2, there is no problem. Then gamma 1 and 2 like this, and gamma 1 3 and gamma 2 3 for the present cylindrical shell case. So, for if somebody is giving a write up for a cylindrical shell, the first step is to give the strain displacement relations for a cylindrical shells. Then see that writing epsilon f1 in terms of these things, that is the most appropriate form for working. If we write the shell constitutive relations like this, so we can directly work out. If we write in terms of a epsilon 110, then again we have to convert into a displacement form and use that. So, this is the most convenient form of shell constitutive relations. Now, we can, like in first equation, nxx comma x plus n theta x comma theta by r. So, let me just go back, nxx this term, n theta x a6612 this term and this term and these two. So, we can write that a11 u1 comma x derivative double derivative a12 1 by r second term, then B matrix, then n theta x A matrix and B matrix. So, in this way the first equation is represented in terms of a primary displacement variables. Same way in the second equation, n theta theta comma theta divided by r, n x theta comma theta plus q theta by r. So, if we substitute using the cell constitutive relations, it becomes like this, plus the non-linear terms, which is n to 2 by r square and this one, and n tilde 1 to w comma x and q2. Then the third equation, these non-linear terms remains, we have to substitute the value of n theta theta, qx comma x, q theta comma r and all these things together. So, our third equation, and substituting in the mx, fourth equation and fifth equation. Now, you see that can we write in a matrix form so that working with these terms will be easy and even that coding will be easy. So, we are trying to do in such a way that arranging the matrix like coefficient of u1 0, 1 and this will kept together. Then the coefficient of u2 0, only 1 and this. Then the coefficient of a w, this. The coefficient of psi 1, let us say different symbol, and this is delta, then this again psi 1 and the coefficient of 2. So, if we do so, we can arrange in a matrix form, and then this matrix form is L11, L12, L13, L14, L15, and these are the our primary variables, and these are the terms related to our non-linear buckling ones, and then in the third. So, basically for the cylindrical shell case, only second and third equation contains terms related to buckling, and these are the loading, and this is our inertia matrix. So, we can write L u plus L b u equal to q plus I u double dot. This is our journal equation where L is a 5 by 5 matrix, and this is 5 cross 1, 5 cross 5, 5 cross 1, 5 cross 1, 5 cross 5, 5 cross 1. Now, what is L11, L22? So, explicitly we can say L11 can be written like this. So, here if you see 1 2, 1 3, 1 4 and 1 5, that 2 1 is nothing but equal to, in this case, because in cylindrical shells we cannot say generally these terms may be symmetric, that L12 is equal to L22 or L13 is equal to L31, but for the present case for a cylindrical shell, sometimes it is exactly same like I can say that 1331. So, sometimes it may be same or with some minus sign. So, that is why we have written all the terms, so that there will be no confusion that whether it is all symmetric or non-symmetric, but for the case of a plate, there this matrix is completely symmetric, there will be no ambiguity. Here the reason behind non-symmetry is that in one direction it is r is infinity and another direction there is r. So, due to that there will be some mismatch, like we can say that n12 not equal to n21. If these are not equal, then L21 cannot be equal to L12, L22, L23, L24, L25, L31, 32. So, this is very important concept for developers, that first find out these L1, L12 and buckling and the inertia matrix, where we know that I0 is minus h by 2 2 plus h by 2 rho times 1 plus z by r, 1 plus z by r into dz, r1 and r2 basically. I1 is rho times zeta times same thing, and I2 is z squares. So, in this way we can find out all the components and we can put it here. Now, what are the boundary conditions? So, previously for the case of when we considered on a linear part, So, we have all neglected this. Even in the boundary there are some non-linear term exist. You may miss these things, because when you go for a linear one, then you just say that either n22 is 0 or u20 is 0, or n21 is 0 or u11 is 0, m22 is 0 or psi2 is 0, m21 is 0 or psi1 is 0, or you can say that q2 is or w0. But for the case of a nonlinear, some nonlinear terms are also there in the boundary. Whenever we are going to satisfy, means free condition of a shell, then it will not just q theta or q x is going to be 0. So, we need to satisfy some more term also, combination of that. So, for that case, when a edge where beta is constant, so if you say that if this is my beta and alpha, so this edge beta is increasing. So, over this, that here beta 1, beta 2, beta 3. So, these lines are corresponding to beta constant. So, the edge where beta is constant, following variables need to be specified, and for the present case the corresponding terms, that n hat 22 and n122 need to be considered. The most important part is there in most of the buckling cases, when we talk about that cylindrical shell is subjected to the axial load, and what is that axial load? That is corresponding to nxx hat only. There will be no n theta theta, no circumferential loading. So, in that case these terms may not come into the picture. But if you say that these n theta theta may also be there, then n theta nx theta is also there combined, then you have to consider these terms. When you see the buckling papers or books, you do not find these nonlinear terms, because they have assumed that cell or cylindrical shell is subjected to the only initial axial stress. So, n hat xx, you can say that n critical or nx naught, whatever you want to say, but nyy and or n theta theta, nx theta is going to be 0, that they are not taking. So, due to that reason these terms are not contributing. But in actual, when you say that okay, there may be some circumferential, yes, if you talk about a cylinder under external pressure or internal pressure, in that case n theta theta may act. So, for that purpose these boundary condition may, so there may be a loading due to the external pressure, outside pressure or internal pressure, then circumferential stress may exist, and we can say that bending due to that. Ultimately this n theta theta cause the bending into the shell. Though shell is subjected to the external pressure, but that external pressure is causing a n theta theta, and due to that n theta theta buckling may takes place. Similarly, when a alpha edge, means this edge where alpha is constant, so that as some more terms may come up. So, if we consider for our present case, yes, this term will may exist, n hat 11 r into w comma x and n tilde 12 and this one. So, along that edge x0 and xa, or you may say that alpha, these terms need to satisfied plus whatever initial stress you have. So, in this way we have to see clearly that what we are going to be satisfied. So, boundary condition need to be modified or need to consider the nonlinear terms when we are going to study a buckling. Even that concept of buckling is done by the linearized buckling and nonlinear buckling. So, present case comes about that we are considering a nonlinear terms, and von Karman nonlinearity is considered, and the buckling effect is studied. Now that very general solution that a shell is subjected to, if we talk about a finite cylindrical shell, because when it is a closed condition, closed boundary, then only one edge x0 or xl is maybe there, or there will be no edge. So, in that case the solution is written, but when we talk about a finite shell panel, when we have a both edges are free, means we can apply the boundary conditions. If that is the case, if we assume that cylindrical finite shell panel is subjected to all simply supported boundary condition, and for that case the deflections is expressed into double Fourier sine series, and in plane displacement is cosine and sine series, and u20 is sine and cosine series. So, in this way these are expressed. Again we have already taken the concept of means time derivative. So, we can say that cos omega t will also be there, the time that how this will vary along the cos omega t. So, if you substitute this expression into the previous one in these equations in L1, L2, L13, so they becomes a new constant, and these constants are known as K, K11, K12, and these are known as K1, K22b, and I becomes M again, because this becomes I0 omega square. So, the positions like this. So, K11, K12, you can see that they may contain M or N. So, basically M bar is M pi x by A, N bar is N pi theta by alpha or theta by psi, whatever you want to say. So, here x is not there, M pi by A and N pi by alpha. So, these are converted. Now, this K is a constant matrix, and this contains some like K43, basically n hat 11 and some K22b, K23 like that. So, we can say that we can write finally set of equations like this K capital U plus Kg Qumn, and this is a complete governing equations. It contains mechanical loading, inertia terms, buckling loading. So, for the case of a static, buckling and inertia terms are neglected. So, this equation reduces to Ku is equal to small q, and Umn can be find it out K inverse into Q. If we want to study a free vibration of a shell, then buckling will be 0, Q will be 0, and Ku will be equal to Mu. So, M is basically I into omega square minus of that. So, if you put this side, so we will say that Umn cannot be 0, so this need to be 0. So, K minus whatever I omega square. So, omega is unknown to you, you do not know the natural frequency. So, basically K upon may I omega square can be find it out, or if it is a single one K upon I, otherwise you write K into I of inverse basically. So, you get 5 frequencies will be known for a simply supported cylindrical panel. Now, we come to the buckling. So, for the buckling case, that Q are 0 and inertia terms are considered 0. Now, our equation is reduces to like this Kumn plus Kgu, where Kg contains n hat 11, n hat 22, n tilde 12. We have 3 terms. So, if we put so and equate to 0, we say that the trivial solution will be all Umn 0, that cannot be. So, it means non-trivial solution will exist when this determinant is going to be 0. So, when we put this determinant is 0, so it contains n hat 11, n hat 22. So, depending upon the case. So, we solve one case at a time. Let us say we consider a cylindrical cell is subjected to axial loading only. So, in that case n hat 11 is n0 and all n hat 22 and n tilde 12 is going to be 0. So, ultimately characteristic equation come up, and from there we can find out n critical loading for the present case. So, in the next lecture I shall discuss for different cases, that under axial load, under external pressure, under thermal load or under combined effect, that buckling of the shells. So, thank you very much.